complex matrix. So you've got 2 plus I, you've got minus 2 plus I, you have I, and you have 4I. So this is question 16 from last year's exam, and you have to get the determinant of A. Okay, so now you look at this thing again. Now don't be afraid of this, because you got a matrix with complex entries. Now this doesn't happen that often, actually, to be fair. In analysis, you rarely get a complex matrix, but sometimes you do, but very rarely do you actually get a complex matrix. But if you have a matrix with complex numbers in it, the rules are exactly the same. So do not be put off by this. We want to get the determinant of a 2 by 2 matrix. So you just write down this thing here. So you get 2 plus I, minus 2 plus I, and 4I. Now, guys, there's no setting equal to 0 here, because you're not getting eigenvalues. You just get the determinant of this. Okay, and how do you get the determinant 2 by 2 matrix? Well, you multiply this by this minus this by this. Okay, so the determinant is 2 plus I by 4I. So it's 4I into 2 plus I minus I times minus 2 plus I. And that's it. So what I wanted people to do there was I just wanted people just to follow the rules. Okay, because that's what mathematics is. Mathematics is just rules. And everyone knows what the rules are. It's like living at home. Everyone knows what the rules are, so just to follow the rules and everybody's happy. If you break the rules, then unhappiness follows, and that's just the way it works. So then you multiply this out. So 4I by 2, so that's 8I plus 4I squared, and then when you multiply this in here, minus gives you plus 2I squared. Oh no, sorry, folks, that's not right. This is minus 2 by I, so that's plus 2I minus I squared. The important rule in complex numbers is that I squared is equal to minus 1 by definition. You've got 8I plus 2I here, so you got 8 sheep plus 2 sheep. How many sheep do you have? You've got 10 sheep, so that you write this as 10I. And I squared is minus 1 here, and minus 1 here. So here's minus 4 minus 1. Be careful with complex numbers and the minuses. So I think when you multiply that, that's minus 3. So I think you get minus 3 plus 10I. So you get a complex number as your solution to the determinant problem. And that was answer D for question 16. So that's what you get. Now we're going to come back tomorrow and we'll talk about complex numbers. But I just wanted to introduce you to them today. You've seen this already in secondary school. Maybe it was taught badly to you. Maybe it was taught well. Maybe it's taught better than I'm going to teach it. It's not. That's a definite possibility. But complex numbers are nothing to be afraid of, and they are very useful, even though they don't exist. But they crop up quite a bit in engineering analysis, especially for those of you who are going into electronics. Bizarrely enough, you use complex numbers probably more often than the mechanical people do, because you're smarter. Let's face it, mechanical guys just want to, they just hit things with hammers, whereas the electronics people, you're much more sophisticated, and I respect you more. Let's be honest. All right, let's go on and do the long questions from last year's exam, if we could. I just want to show you how these work as well. These look difficult. They're not. They're really not, guys. They're difficult because you're seeing this material for the first time, but they're not difficult at all if you keep your heads and follow the rules. That's basically what I'm saying to you this morning. My message to you this morning is follow the rules. Okay? So I'm not going to do Connor's questions because I can't do them, but let me just do the longer questions too from last year's exam, just to show you that I can do these. I hope I can anyway. So the first question that you asked for was, show that the eigenvalues of, here's the matrix, 0, 0, minus 2 beta, 0, 0, beta, minus 2 beta, beta 0, are 0, and plus or minus beta root 5. Now, as I said, guys, back in the day when I was a young man and I had no friends, and even this was a bit of a challenge. Look, I did have a little bit of mathematical ability, but not very much, and I was always a bit intimidated by these kind of questions at the beginning because I didn't really understand what eigenvalues were. I wanted to understand them more or something. I don't know. I had a kind of a block with this. I don't want you to have the same block, basically. All you're being asked to do here is apply a recipe. That's it. Just follow the rules. I think that's when I kind of learned how to be a mathematician, or supposed to, or think like a mathematician at least. Was just appreciate these are rules. Everyone knows what the rules are. Don't make up your own rules. Follow the rules that everybody else is using. Okay, so that's what I'm going to do here. So remember what we do. What you're doing in here, guys, is you take your square matrix. In this case, it's a 3 by 3. And you replace the square brackets by the straight line brackets because we're going to be getting a determinant. Because we're talking about eigenvalues, we're going to be setting the determinant equal to 0. Now, remember now, guys, the distinction between question 16, where you just ask for the determinant of A, which was just this, but there's no equal to 0 business here. Don't always set the determinant equal to 0. You only set the determinant equal to 0 when you're looking for eigenvalues. So on what do you set equal to 0 here? Well, you write down your square matrix here. And from the main diagonal elements, you subtract lambda. So you're getting 0 minus lambda, 0 minus lambda, 0 minus lambda. So what I'm going to do now is I'm going to replace the 0 by minus lambda, and minus lambda. And the question then arises, well, why do you do that? Because that's what you do. That's it. That's the recipe. Okay? And once you do that, then everything else is simple. So I don't know how many marks there was going for this from last year. Again, my phone just keeps dying on me here. But if you look at the how many marks we're going for this, there's 6 marks for this, guys. This is just a steal, right? Because it's just a recipe. You subtract lambda from the main diagonal elements, so you get 0 minus lambda, 0 minus lambda, 0 minus lambda. So you get minus lambda, minus lambda. And then what you do is you just do the determinant and set the thing equal to 0. So therefore, you look at the first element here, which is minus lambda, and you write it down. What do you multiply minus lambda by? You cover up the first row, the first column, and you multiply minus lambda by lambda, which gives you lambda squared, and then beta by beta minus beta squared. The second element is 0, so we don't have to worry about the minus 0 here, and we don't have to worry about actually doing any multiplication because the element is 0, so we just ignore it. The final element is minus 2 beta, and I write that down. And what you get then here is you get 0 by beta, which is 0, minus lambda by 2 beta is plus 2 lambda beta. So lambda by 2 beta gives you 2 lambda beta. And it's minus because minus by minus gives you plus. Okay? And you set that equal to 0. That's what it is, folks. There you are. That's it. So you multiply that out then. And so what you get then, if I could do that up here, so if I just multiply in here, I'm going to get, if I go up here, sorry, so you get minus lambda cubed plus lambda beta squared. And this here, guys, is minus by minus plus, because plus 4 beta squared lambda equal to 0. Okay, so now you're messing about all right with symbols rather than numbers, and that takes a little bit of getting used to. But it's the same thing here. Now, if you look at here, you've got a lambda beta squared, you've got a lambda beta squared here. So this term is the same as this term. You've got 1 here and you've got 4 here. So when you add this to this, you get 5. So what you get then is you get minus lambda cubed plus 5 lambda beta squared is equal to 0. If I can come on to the next page, then I'm getting so minus lambda cubed plus 5 lambda beta squared is equal to 0. There's a common term here. There's a lambda common, so I bring that outside. So I get lambda into minus lambda squared plus 5 beta squared is equal to 0. So now what I have is I've got the product of 2 things equal to 0. So when you multiply 2 things, you get 0. One or both must be 0. So let's look at the situation where both could be 0. So look, so the first solution I get to this equation here is lambda equal to 0. Because lambda is equal to 0. The second solution I get then is minus lambda squared plus 5 beta is equal to 0. So therefore, lambda squared is equal to 5 beta squared. So therefore, then lambda is equal to plus or minus beta by the square root of 5. And that's what you have to show. So that's QED. Okay? So this was not too difficult. You did have to mess about with symbols, but that was all you had to do. And in the end, folks, remember what we're trying to get here. We're trying to get what lambda is. Okay, we assume we know what beta is. Okay, so we're trying to get what lambda is. So we know one value for lambda could be 0, and the other two values could be plus or minus beta root 5. And that's the solution to question 2a. I'm going to do question 2b for you now, if I could. So question 2b then is you have to find the eigenvectors for these eigenvalues now for question 2b. Now, this is a little bit stranger. This is a little bit strange, I do admit. But let me just show you how it is. This is question 2b. So remember now what we've got. We've got the eigenvalues of 0. We have beta root 5, and we have minus beta root 5. And what we have to do then is we have to get the eigenvectors corresponding to each of these eigenvalues. So the first thing you do then is you remember what an eigenvector is. An eigenvector is ax equal to lambda x. We don't know what x is. We know and lambda is the eigenvalue. So the first case we put in 0. We put in lambda equal to 0. So when I put lambda equal to 0 here, folks, I'm going to get ax is equal to 0. Okay? Because 0 by a column vector is always going to be the column vector with zeros. So, and I denote the column vector of zeros by 0. So then what I would do is I put in a, which in this case is just a is just the 2 by 2 matrix that you got. So what you have here, guys, is we've got 0, 0, minus 2 beta, 0, 0, beta, minus 2 beta, beta 0. X is the eigenvector, which we don't know what it is yet. Let's call it x, y, and z, and that's equal to 0, 0, 0. Okay. So, and the reason why you're getting all zeros here is because for the eigenvalue of lambda equal to 0, the right-hand side becomes zeros. Okay, so you get ax equal to 0. So you get, you multiply a, which is the matrix that you're given. In this case, 3 by 3 matrix, which you're given, and you're getting this matrix here. So if you multiply, again, can I come up here, guys, just to save paper? If I multiply out the first, get the first equation here, I get 0 by x, which is 0. 0 by y, which is 0, minus 2 beta z equal to 0. So the first equation that I get from this matrix equation is I get 0 by x plus 0 by y minus 2 beta z is equal to 0. Okay, so that's the first equation here. So 0 by x plus 0 by y minus 2 beta z equal to 0, and that's what I get. And 0 by x is 0, 0 by y is 0. So what I get here, guys, I don't know what beta is. Beta is just any number. So therefore, from the first equation here, I get z is equal to 0. The second equation, I get 0 by x plus 0 by y plus beta z equal to 0. So then I get, again here, I get z is equal to 0. So that's okay, because whenever you get redundancy when you're calculating eigenvalues, only 2 of the equations give you information. So the two of the equations will give you the same thing, and that's what we get here. And finally, then the last equation here, guys, gives me minus 2 beta x plus beta y plus 0 by z, which is 0, equal to 0. I bring the beta outside. I get y minus 2x is equal to 0. Beta can be any value you like, so that means it can't be 0. It's not, so therefore what you get here is you get y is equal to 2x. So in this case then, your eigenvector corresponding to lambda equal to 0 is the eigenvector is x, y, z. We know that z is equal to 0 from the first two equations here. And we know that y is equal to 2x. So what you get here, guys, is you get x, 2x, 0, and you can bring the x outside if you want to, and you get 1, 2, 0. So x by 1, 2, 0, or just as 1, 2, 0, that's fine as well. So that's the first eigenvector. That's the eigenvector corresponding to lambda equal to 0. Okay, the second eigenvector then is beta. Lambda is equal to beta root 5. Okay? So what you do then in this case, guys, is you must put in ax is equal to lambda x again. X is the eigenvector, which you don't know. A is the square matrix, which you're given, and lambda is the eigenvalue. So in this case, what you get is 0, 0, minus 2 beta, 0, 0, beta, minus 2 beta, beta 0, x, y, z is equal to beta root 5. My pen is running out. So you get that, okay? So all I've done there is I've replaced A by whatever it is, which in this case is the matrix that you're given. I've replaced X, the vector X, by X, Y, and Z, because I know it must be a 3 vector, because we were talking about A is a 3 by 3 square matrix. So the eigenvector must be a 3 by 1. And lambda is the eigenvector, which in this case is beta root 5. So when I do this calculation here, I'm going to get 0 by x for the first equation I get here. I get 0 by x plus 0 by y minus 2 beta z is equal to beta root 5z. Okay? The second equation, I'm going to get 0 by x by 0 by y plus beta z is equal to beta root 5z. And finally, I'm going to get minus 2 beta y, minus 2 beta x plus beta y plus 0 z is equal to beta root 5z. So let me see when I multiply that out, what I get. So the first equation gives me this. So I'm going to get 0 by x plus 0 by y minus 2 beta z is equal to beta root 5x. Sorry, I think I made a mistake when I was bullshitting there beforehand. So what you do is you multiply out the first row by this column here, and you set it equal to the first entry here, which is beta root 5x. So I'm getting 0 by x plus 0 by y minus 2 beta z equal to beta root 5x. Okay, so that goes to 0. I guess that goes to 0. I've got a beta term here common, so I can get rid of that, cancel it. So what I'm getting here then is I'm getting minus 2z is equal to root 5x. So therefore then I'm getting z then is equal to minus root 5 over 2x, which is kind of horrible, but that's what it is. Okay, so I'm getting z is equal to minus root 5 over 2x. That's the first entry. That's what the first equation tells me. Let's look at the second equation here. So this is kind of long-winded. I know it is long-winded, but you do get quicker when you're doing this, guys. So this is the first equation. The second equation tells you that 0 by x plus 0 by y plus 0 by x plus 0 by y plus beta z is equal to beta root 5y. Okay? And so then you got this you cancel, this goes to 0 as well, and the betas will cancel. So I'm left with z is equal to root 5y. Okay, so I've got z is equal to root 5y. I've got z is equal to minus root 5 over 2x. So therefore, this is equal to this. And the root 5s will cancel here. So therefore, I'm getting y is equal to minus x over 2. Now, you can use the last equation. You can go to the third equation if you want to, but there is no point because you know that the third equation is going to be just going to be either this or this. So there's no point in going to the third equation. So you can save yourself some time. So basically what you've done here is from the first equation, you've got z in terms of x. From the second equation, you've got y in terms of x. So your eigenvector, folks, is x, y, z. And we know what everything is in terms of x now. Y is minus x over 2, and z is minus root 5 over 2x, and that's your eigenvector. And you can bring the x outside if you want to. So you get x times 1 minus a half minus root 5 over 2 if you wanted to do that. Okay. So I do appreciate that this is a bit tedious and this is a bit unnatural even, but that's what you get. So don't be afraid of this. Okay, I'm not going to do the last one, lambda equal to minus root 5, lambda equal to minus beta root 5. It's pretty much the same thing here. You just get plus signs here instead of minus signs, but I'm not going to go into it. Okay, so it's exactly the same thing. So this question, I do appreciate that question 2b was a little bit tricky. because it involved eigenvectors, and eigenvectors are always difficult when you first see them the first time. When you see them for the first time even. So just work through it. Be brave. You will get there, and it is important to be able to calculate eigenvectors. And it's very unusual as well. Be careful with the eigenvector calculation. Is that one of the equations will be redundant? And if you look at the situation here, you've got 3 equations and 3 unknowns. But really, what this is just 2 equations and 3 unknowns. One of the equations won't give you any extra information, and that takes a little bit of getting used to. It's the first time you've seen this in mathematics, but it's an important little idea as well. Okay. Finally, guys, let me do question 2, part C, and just show you what it is and how easy it is, and we're going to stop here, I think. And we'll start talking about complex numbers tomorrow. So question 2, part C was pretty straightforward, actually. It involved complex numbers, so again, this is kind of an introduction to what we're going to be doing tomorrow. So, again, it was a 3x3 matrix, but in this case, it was complex matrix. So H was 1 minus I, 1 plus I, 2I. It was 1 minus I, 5 and minus 3. And it was minus 2I minus 3, 0. Okay, so it was a complex matrix. It's a complex square matrix. It's a complex 3x3 matrix. And the first thing you were asked, guys, for was H transpose. Now, guys, this is just like, come on, there's no excuse for not doing this. Now, I know there's complex numbers in the matrix, and so therefore you might be a little bit intimidated by that, but you shouldn't be. It's exactly the same thing. The first row becomes the first column. So you get 1 plus I and 2I here. That's it. That's all you do. Whatever the first row is becomes the first column. The second row becomes the second column. So the second row is 1 minus I, 5 minus 3, and the third row becomes the third column. And if you did that, simple calculation, you got 3 marks. I'm beginning to wonder if I'm actually the way I used to be a lot tougher than this, folks. There was 3 marks for this. It's shameful if you didn't get marks for this. And I'm thinking back to last year's exam. I think people were intimidated by the fact that it was a matrix of complex numbers, but it doesn't matter. It's just exactly the same rules. Just follow the rules. Okay. And the last part then of this question was to get the complex conjugate. Now we haven't talked about this, but we're going to be talking. I will talk about it now. Just kind of set seeds in your brain. If you've got a complex number, the complex conjugate means you change the sign of the I term. That's all it is. So what you do here, 1 is not a complex number, so you can't get the complex conjugate of that. So let me call the complex conjugate H transpose bar, because that's just stupid notation. It doesn't matter what you do, what you call it. I'm going to call it H transpose bar, because that's the traditional notation in engineering. So you go to each of these numbers. If it's a complex number, you change the sign of the I term. If it's not a complex number, you leave it alone. So 1, you just leave it alone. 1 minus I, you change the minus I to plus I, because that's what the complex conjugate is. Here, minus 2I, you change the sign of the I term, and you get 2I. Here, you change the sign here. It's 1 minus I. 5 you leave as it is. Minus 3 you leave as it is. Minus 2I, you change that. You change you leave the minus 3 alone, and you get 0. And that's it. You've got 3 marks for that as well. Oh, come on. And you notice here, folks, that H and H transpose bar, the conjugate of the transpose are the same. This is exactly the same as this. And this is a very important idea in physics, in certain parts of physics, in quantum physics, actually, quantum mechanics. This is called a Hermitian matrix. You don't give a shit what it's called, really. So just backtrack there, just edit that word out. You don't care what it's called, but these kind of matrices are important in physics. And you might see them again if you're working in electronics, because there's a very big overlap between electronics and physics, not so much with mechanical. So, but basically all I asked you to do in that question, folks, was 6 marks, get the transpose and then get the conjugate. And the conjugate is where if you have an I term, you change the sign. That's it. Come on, 6 marks. You're into second year. And then I torment you in second year. But like, at least you're in second year, all right? So get on top of this. So that was the 2019 exam as a review. All right. At the end of next week, when I'm wrapping up, I will do hopefully the repeat exam for 2019 and just show you what that is and do the whole thing for you. Tomorrow when we're going to start complex numbers. We've actually started complex numbers and we've got the main ideas already in your brains. This idea of a conjugate, which is very straightforward, and the idea of what a complex number is and where it comes from. It comes from a quadratic equation where you don't have real roots. And you call the sign, you call the square root of -1, you call that I, and then you see what happens once you do that. And just that rule, that the square root of -1 is equal to I, amazing things follow. Very, very unusual things follow. And it's going to be exciting. You're going to love it. All right, guys, I will talk to you tomorrow. Comics numbers tomorrow, guys. Tune in. All right, bye.